warahmatullahi wabarakatuh. My name is Abdullah Faid bin Ahmad Kamal. My ID number is 214745. So my part in this project, I'm gonna simulate about FM demodulator. So let's continue with node 1, which is FM source input. So the input voltage is an FM modulating signal with peak amplitude 3.5 volt, carrier frequency is 35 kilohertz, and modulating frequency is 600 hertz. So the waveform is an FM carrier signal, which instantaneous frequency varies according to the 600 hertz modulation signal. So this form the base of the system for analysis. So the current through resistor 1 depends on the applied voltage and resistance. So which is I is equal to V over R. So 3.5 over 470, which is we got 7.45 milliampere. So that's the current flow from the FM source through R1 and into the pre-filter stage. So the waveform description, a high frequency 35 kilohertz signal with a slower 600 hertz envelope. So the modulating signal creates frequency deviation in the carrier wave. So let's continue with the node 2. So after resistor 1 and capacitor 1, the signal undergoes high pass filtering. So R1 and C1 form a high pass filter that attenuate lower frequencies while passing the modulated high frequency FM. So the voltage at node 2 will still reflect the FM modulated signal but with reduced low frequency noise. So the the capacitor C1 impedance is frequency dependent, which is the calculation that I got is the formula is XC is equal to 1 over 2 pi FC, which is 1 over 2 pi 35 kilohertz times 15 for the capacitor. So we got the answer is 303 ohms. So the current through C1, so the formula is I is equal to V over XC. So 3.5 over 303, the answer just now we got. So the answer is 11.55 milliampere. So the waveform at node 2 retain the FM characteristic but with reduced noise due to the filtering action at C1. So let's continue with the operational amplitude. So the operational amplitude amplified the signal from node 2. The voltage at node 3 is negative 1.893 volt as shown in the simulation. So the amplification depends on the operational amplitude gain configuration. So the provide current to the diode D1 over here and R2. I'm using the formula I is equal to V over R2, which is the voltage we got at node 3, which is negative 1.893 over 30. So the answer is negative 63.1 milliampere. So the output for the waveform, the output is an amplified version of the modulating signal with the FM carrier and its envelope visible. So let's continue with the node 4. So after the diode D1, the signal become rectified. So retaining only the positive or negative half cycles. So the voltage at this point represent the envelope of the FM signal, primarily the 600 hertz modulation. So the current flow through R1 into rectification stage. I'm using also the I is equal to V over R, so which is 1.893 over 30, which is 63.1 milliampere. So the waveform is a rectified version of the amplified FM signal, showing peaks corresponding to the 600 hertz envelope. So at the node 5, after the smoothing filter formed by capacitor 2 and resistor 3, the signal becomes a clean 600 Hz sine wave representing the demodulated modulation signal. So voltage at this envelope signal with reduced voltage at this node is the envelope of the rectified signal with reduced ripples.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Asmi Zubair Azaman and my metric number is 215750. So today I'm going to demonstrate a simulation for uh, FM modulation and FM demodulation. So first of all, the upper part will be our modulation part, this upper part, and then this lower part will be our demodulation. So this V5 will be our carrier frequency, whereas this V4 will be our modulating frequency. So this carrier frequency and modulating frequency will be going through a modulator, which is a transistor effect, and then it will come out of the collector. So this collector will be going through a 10 circuit, which will be act as a resonant filter. So this resonant filter, we only filtering out a signal, which is around 1.68 megahertz. So after that, we'll be having our FM modulation signal, which is this part, this yellow part, and then after that we'll be going through our demodulation process. So this C3 and R5 will be, and then this low part, this C3 and R5 and R6 and C4 and C5 will be our demodulation part. So the C3, R5 and R6, C4 and C5 will be our band pass filter. So it will be consist of filtering out the high pass and low pass filter. So and then the D1 will be act as our rectifying. So it will rectify the signals. So it will smoothing out the signal, and then the C7 and C6 will help smoothing out the signal. So let me show you the simulation through the oscilloscope. So let's run the simulation itself. So alright, as you can see, let me pause the simulation. So as you can see, so the upper part will be our carry signal, and then this part will be our modulating signal. So and then the yellow part, this yellow part will be our FM modulation, and then the lower part will be our demodulated signal. So it almost follows the original modulating signal, but due to some variation in the in the circuit, so the energy might be lost, and then the modulation might be not as perfect as it should be. So the next one, I'm going to uh, s- simulate a difference variation that will cause the having the signal perfectly demodulating the FM signal. So let me run it again. Right. So let me pause it again. So as you can see, so we look at the green color one. So the green color one is the channel V. So if you look closely, let's see, let's try pin on that. So the modulating signal is not as perfect. So if you can see, it's not demodulating perfectly. So meaning that the the signal is not being perfectly the same as the channel B, meaning we got losses. So as you can see, the channel D, the value would be should be the same as modulating signal, but it's not. So if you look at the channel D values, it's fluctuates between 3.97 and 1.349 millivolts. It should be volts, but it's not. So let me show you the variation that will cause the signal to have a perfect, almost to perfect demodulation. Okay, so I'm going to show the simulation where we change the value for the two key components that most likely will change the value for our demodulation part. So the first part is I'm assuming this R4 will be our one of the key components that will change our demodulation signal. And then this C3 will be changing our demodulation part as well, our capacitor. So I'll change the value of R4 around the modulation part. I'm sorry, the modulating signal around 1 ohms. Whereas this one will be, the C3 will be 3 microfarad. So if we run this simulation again, so as you can see, the the current value now spikes. So if we look at the current value, so if you look at the value, the value now fluctuates between 1.183 volts till negative something like that. So the highest peak value that we can get is around 1 volts. So it shows that we almost get to the threshold of demodulation, the perfect demodulation of FM. So let me run it again, but with different value. The next one, I'm going to show you the I think the value of threshold that we can reach, that from these two main components that I think they're going to change our demodulation effectiveness. So let me try to run it again. So I changed the value to R4. R4 still the same of 1 ohms, whereas the C3, the capacitor, I changed it to 100 micro ohms. So let's try and see what's the signal would look like. So this is what the signal will look like if we change that value. So the most value that we can get is around 1.341 volts. So compared to the previous one, we only get around 1.13, 1.1 volts. So it shows that those two components are effectively can change our effectiveness to demodulate the FM signal. So although this is our threshold, so without a amplifier, so we cannot amplify the signal to reach our original signal. So in order to do that, we need to have a amplifier.